Welcome back to the deep dive. Today, we are doing something a little different.
Yeah.
Usually, we look at a specific event or a trend or, a piece of history. But today, we are tackling the stage itself, the board on which the game of life is played. We are talking about the ocean.
All of it.
All of it. And I don't just mean the beach you go to on vacation. I mean the engine that drives this entire planet.
It's the defining feature of our world. I mean, if you were an alien astronomer looking at our solar system from light years away, you wouldn't call this place Earth.
No.
You'd call it ocean.
That's actually the exact argument Fabien Cousteau makes in the foreword of the material we're looking at today.
Right.
He basically says, we've misnamed our own home. We call it Earth, which is dirt, ground, soil, but that's just the little crust we cling to. The planet is water.
It's a profound perspective shift, isn't it?
Yeah.
When you look at that famous blue marble photo, you see this vibrant sapphire sphere just floating in this incredibly hostile, cold, dead universe. That blue is a beacon. Cousteau calls it the Petri dish. He points out that the ocean isn't just a place with life. It is the source of all known life. Without that liquid water, we are just another scarred rock like Mars or the moon.
And we have this tendency to think of ourselves as the dominant species, the main characters of the story. But biologically speaking, we are the minority tenants living in the attic.
Ah, that's a good way to put it.
The stats are just humbling. Over 90% of the world's biodiversity resides in the oceans. 90%. We're all fighting for space on these little dry scraps of land while the real party is happening downstairs.
And the craziest part?
Yeah.
We don't even know who's at the party.
Not at all.
We have mapped the surface of Mars and the dark side of the moon with higher resolution than we have mapped the floor of our own ocean. It is the last great terrestrial frontier.
Exactly.
But the goal of this deep dive isn't just to say, wow, it's big. We want to understand the machine. We want to take a shortcut through the chemistry, the geology, the physics, to really get how this life support system actually functions.
So to understand the machine, we have to start with the blueprint. And the blueprint of the ocean is the water molecule itself. Now, I know everyone listening knows the formula H2O,
Right.
2 hydrogen, 1 oxygen. It seems simple, but it's actually a really, really weird molecule.
It is incredibly weird.
Yeah.
I mean, if water behaved like other molecules of its size and weight, it should be a gas at room temperature.
A gas.
Yeah. The oceans just shouldn't exist. The only reason we aren't living on some cloud-covered dry rock is because of the very specific shape and the electrical charge of that one molecule.
This is the dipolar concept, right? I always think of it like a tiny magnet.
That's the perfect analogy. You have that big oxygen atom, and it's an electron hog. It's greedy. It pulls the negatively charged electrons toward itself, which leaves the 2 little hydrogen atoms slightly positive.
So the molecule has a positive side and a negative side. It has 2 poles. It's dipolar.
Exactly. And just like with magnets, opposites attract. The positive ear of one water molecule grabs onto the negative face of the next one.
Okay, so they all just sort of link up.
They link up. This is called a hydrogen bond. Now, individually, these bonds are, they're weak. They break and reform constantly, billions of times a second.
So they're not very strong on their own.
Not at all.
Yeah.
But collectively. When you have trillions upon trillions of them all pulling together, they are incredibly powerful. This stickiness is what keeps water liquid. It's what creates surface tension.
Ah, surface tension.
Yeah.
That's one of those things we see every day but probably don't think about. You see a raindrop on a window and it holds that nice round shape.
That's it.
That's the hydrogen bonds pulling all the surface molecules inward, creating a sort of skin.
It is a skin, effectively, a real physical barrier. And nature is absolutely brilliant at exploiting physics. There are entire ecosystems that live on this skin.
You're talking about things like the water strider.
The sea skater, the water strider, exactly. These insects are heavy enough that they should sink. They should break right through.
Yeah.
But they've evolved to distribute their weight perfectly so they don't break those hydrogen bonds. They walk, they feed, and they even mate on top of the open ocean, separated from the abyss by nothing but molecular attraction.
It's wild to think about. If those bonds were just a tiny bit weaker, those bugs would drown.
Instantly.
But it's not just about bugs walking on water, right? This stickiness is the reason biological life as we know it can even work.
Oh, absolutely. Think about a giant redwood tree, or even just a blade of grass in your yard. How does water get from the roots all the way up to the leaves against gravity?
It doesn't have a heart to pump it.
Right. It relies on the fact that water molecules stick to each other. It's called cohesion. As one water molecule evaporates from a leaf, it pulls the next molecule up the chain behind it like a rope.
A molecular rope.
Without hydrogen bonds, plants couldn't transport nutrients. They'd all be an inch tall.
And neither could we. Our blood is mostly water. If it wasn't sticky and cohesive, our circulatory system just wouldn't work. We are basically walking, talking bags of hydrogen bonds.
You should put that on a t-shirt.
Huh.
But this dipolar nature gives water another superpower, and maybe the most important one for the ocean. It is the universal solvent.
I love this term. It sounds like something from a comic book, a villain's weapon or something. But essentially, it just means water is a molecular homewrecker. It's great at tearing other bonds apart.
It really is.
Yeah.
Think about regular table salt, sodium chloride. In a crystal, those two atoms, sodium and chloride, they're locked together tight.
We're very stable.
But you drop that crystal of salt into water, and the water molecules swarm it. The negative oxygen ends of the water surround the positive sodium atom, and the positive hydrogen ends surround the negative chloride atom.
And they just pull it apart.
They pull them apart. They insulate them from each other. That is what dissolving actually is.
So when we look at the ocean, we aren't just looking at water, we are looking at a chemical soup. It's a solution of everything the water has managed to tear apart over billions of years.
Precisely. And while sodium and chloride are the big players, they make up about 85% of all the dissolved mass. The ocean contains, well, almost every element on the periodic table. Magnesium, calcium, potassium, gold, uranium. It's all there in very, very trace amounts, but it's there.
But here's where it gets really interesting to me. The recipe for this soup is incredibly consistent. I was reading about this guy, Alexander Marseille, a doctor from 1819.
Ah, yes.
He was getting water samples from sailors from all over the world, the Arctic, the Mediterranean, the Atlantic, and he found something that just blew his mind.
The principle of constant proportions.
Exactly.
He realized that while the total amount of salt might change, the Baltic Sea is less salty because of all the river runoff, and the Red Sea is super salty because of evaporation.
Right, the salinity varies.
The salinity varies, but the ratio of the main ingredients never changes.
Right.
The percentage of magnesium relative to the percentage of chloride is the same in the North Pole as it is in the South Pacific.
Which implies that the ocean is one single, massive, well-mixed system. Over geological time, the currents have just blended everything together perfectly. But it's not a static system, is it? It's not just a bucket of salty water sitting there. Stuff is constantly entering and leaving.
Right. It's a dynamic balance of what we call sources and sinks. The source is where the salt comes from.
So rivers.
Rivers are the main conveyor belt. They erode the continents, dissolving rocks. Remember, water is the universal solvent. And carrying those minerals out to the sea. You also get volcanic ash falling on the surface and hydrothermal vents on the seafloor pumping chemicals up directly from the Earth's crust.
So the rivers are constantly salting the ocean. The obvious question then is, why isn't the ocean getting saltier and saltier until it just turns into a solid block of salt?
And that's where the sinks come in. The ocean has ways of removing these elements. Some of it happens physically, waves spray salt onto the land, or certain minerals precipitate out and just fall to the seafloor as sediment.
Okay.
But a huge part of it is biological. Life is a sink.
Right. Animals need these minerals to live. Clams need calcium to build their shells. Tiny organisms called diatoms need silica. They are actively pulling these elements out of the water to build their bodies.
And when they die, those shells and skeletons sink to the bottom and get buried, forming layers of sediment. That removes the material from the water column for millions of years.
So there's a term for this, right? The residence time.
Yes, residence time. It's how long a specific atom or ion stays dissolved in the water before it gets used or buried. Something like chloride has a residence time of millions of years. It just hangs around.
It's something like iron.
Iron gets snatched up by plankton almost instantly. It has a very short residence time because it's so vital for life.
So the chemistry of the ocean is actually controlled in large part by the life within it. It's a massive feedback loop.
It is.
And speaking of life-controlling chemistry, we have to talk about the gases, oxygen and carbon dioxide. Because my assumption was always pretty simple. Surface water has lots of oxygen, deep water has none. But the reality is way more complex.
It is. It's a very layered story. Obviously, the surface is rich in oxygen. You have the atmosphere pressing down on it, dissolving into the water, and you have phytoplankton photosynthesizing in the sunlight, actively pumping out O2.
Okay, so far so good.
But as you descend, you hit a strange layer. Between about 600 and, say, 3,000 feet deep, The oxygen levels just crash.
This is the oxygen minimum zone.
Right. And it happens because of a biological traffic jam. You have all this organic matter-dead plankton, fish poop, what scientists call marine snow, raining down from the surface.
A buffet.
A constant buffet. And in this twilight zone, huge populations of bacteria and other animals are feasting on that falling food.
Right.
And they're all breathing. They're all consuming oxygen and releasing CO2.
But because it's dark, there are no plants down there to replenish the oxygen.
Exactly. So the levels just tank. It's like a super crowded room with all the windows closed. Everyone uses up the air.
But then, and this is the part that I found so counterintuitive, if you keep going deeper, past 3,000 feet, the oxygen actually goes up again, which makes no sense. Who is pumping oxygen into the abyss?
The poles are. This is where chemistry connects to global circulation. Cold water is dense. At the poles, surface water gets super cold, super dense, and it sinks rapidly, plunging right to the bottom of the ocean.
And that water was just at the surface.
It was just at the surface in the Arctic or Antarctic, so it's full of dissolved oxygen. It acts like a giant ventilation shaft, driving this fresh, oxygenated water along the bottom of the entire planet's ocean basins. That's why deep-sea creatures can breathe.
That is a perfect transition to the nutrient cycle, because if the poles are sending oxygen down, something has to bring the food back up.
Yes.
The text mentions nitrates, iron, phosphates, basically the fertilizer of the ocean.
And these nutrients are generally heavy. When things die and decompose, those valuable nutrients end up on the bottom, in the sediment. If they stayed there forever, the surface would eventually starve, and most life would just cease.
So we need a way to reconnect the bottom to the top. We need to get that fertilizer back to the garden.
And that mechanism is called upwelling.
Upwelling.
It is the engine of fertility in the ocean. Along certain coastlines, wind consistently pushes the warm surface water away from the land. And to fill that void, deep, cold, nutrient-rich water rises up from the abyss to replace it.
And when that ancient fertilizer hits the sunlight,
boom, you get a bloom.
A massive explosion of life.
A massive explosion. We have these incredible satellite images of places like the Skagerrak Strait between Denmark and Norway, where the water turns a milky turquoise because trillions of microscopic algae have bloomed all at once.
And that's the base of the entire food chain.
That is the base. No upwelling, no phytoplankton,
Yeah.
no phytoplankton, no fish, no whales, no seabirds. It all starts there.
Okay, so we've established the blood of the planet, the water, the salt, the gases, the nutrients. Now let's look at the body, the geology, the container that holds it all. The source material says the ocean formed over 4 billion years ago. But that brings up a really basic question. Where did all this water come from?
This is one of the great debates in planetary science. The text highlights the two dominant theories, and the real answer is almost certainly a bit of both.
So theory one is the homegrown theory, right?
Right.
From the planet itself.
Yes, that's outgassing.
Right.
When the Earth was first forming, it was a molten hellscape, just a ball of lava. As it started to cool and form a crust, volcanoes were erupting everywhere.
And volcanoes don't just spew lava?
They spew enormous amounts of gas, and a huge percentage of that gas is water vapor, steam.
So the early atmosphere was just thick, hot steam.
Unbelievably thick. But eventually, the Earth's surface cooled enough for that steam to condense into liquid. It started to rain.
The first rain.
And it probably rained for thousands, maybe millions of years. It was the flood to end all floods, filling up all the low basins and creating the very first oceans.
And theory two is the special delivery method.
A space delivery. We know that the early solar system was a chaotic place, and the young Earth was bombarded by comets and icy asteroids. These objects are essentially dirty snowballs from the outer solar system.
They're made of water ice.
Exactly. When they slammed into Earth, they delivered their payload of frozen water. So a significant portion of our oceans was likely delivered from space.
It's just mind-bending to look at a glass of water and think, half of this might have erupted from a prehistoric volcano, and the other half might have come from a comet that traveled billions of miles to get here.
It connects you to the cosmos in a very literal way.
Now let's talk about the crust itself. I think most people, myself included, kind of assume that the ground under the ocean is just like the ground in their backyard, just wetter.
Yeah, that's a common misconception.
But it's not true at all. The ocean floor is a completely different kind of rock than the continents.
There are two fundamentally different types of rock. This is a key concept in geology, the bimodal crust. You have continental crust and you have oceanic crust.
Okay, let's break them down. Continental crust is what we have standing on right now.
Continental crust is thick. It can be 15, 20, up to 40 miles thick in some places. It's made mostly of granite and sedimentary rocks. It's rich in silica and aluminum. But crucially, it is relatively light and less dense.
And it's old.
And it's very old. Some of the rocks on the Canadian Shield are around 4 billion years old. They've been floating around like permanent rafts for almost the entire history of the planet.
And the oceanic crust.
It's the opposite in almost every way. It is very thin, maybe 4 to 7 miles thick at most. It's made of a dark volcanic rock called basalt, which is rich in magnesium and iron.
Which makes it heavy.
That makes it dark, heavy, and dense. And it is very young. You won't find any oceanic crust older than about 200 million years because it's constantly being created and destroyed. It's recycled.
This density difference is why we have oceans in the first place, isn't it? It's a principle of buoyancy.
It's a principle called isostasy. Think of the Earth's mantle, the layer below the crust, as a thick, gooey fluid, like honey or hot tar. The crust floats on top of it.
Okay.
The continental crust is thick but light, so it floats high like a big block of styrofoam. The oceanic crust is thin but heavy, so it sinks low like a thin block of dense wood. The water naturally flows downhill and pools in those low spots. The ocean basins exist because basalt is heavy.
This source material gives us this great cutaway view of the oceanic crust. It's not just a single slab of rock. It actually has distinct layers.
It's a very standardized cake. At the very top, you have what are called pillow lavas, that's basalt, that erupted directly into the cold seawater and cooled instantly in these bulbous, pillow-like shapes.
Right.
Below that, you have sheeted dikes, which are these vertical channels and cracks where the magma pushed its way up towards the surface. And below that is a rock called gabbro, which is chemically the same as basalt, but it cooled slowly deep underground, so it has much bigger crystals.
And at the very bottom of that cake, we hit a boundary with a fantastic name. The Moho.
The Mohorovičić discontinuity. Try saying that 3 times fast. It's named after the Croatian seismologist who discovered it. It's the sharp seismic boundary where the crust ends and the mantle begins.
So everything above the soft, flowing part of the mantle is what we call the lithosphere.
Right. The crust and the very top rigid part of the mantle together form the lithosphere. These are the plates of plate tectonics. They are rigid slabs gliding over the hotter, softer layer below, which is called the asthenosphere.
Okay, so we have the water and we have the container. Now we need to turn the machine on. We need to talk about the engine. Section 3 in our source covers circulation, winds, and waves.
This is where physics starts pushing biology around on a massive scale. And the primary driver of all this movement is the sun.
The sun.
It's that simple. The sun heats the equator way more than it heats the poles. Heat is energy. The atmosphere and the ocean are just giant engines trying to balance that energy out to move heat from the tropics toward the poles.
So hot air rises at the equator and tries to flow toward the poles. And cold air at the poles sinks and tries to flow toward the equator.
In a perfect world, yes. If the Earth were standing still, that would be it. Winds would just blow north and south in these huge, simple loops.
But the Earth is spinning, and that brings us to the Coriolis effect. This is one of those concepts that I feel like everyone nods at, but secretly finds really confusing.
It is tricky, but there's a simple way to think about it. Imagine you are standing on the equator. To go around once in 24 hours, you have to travel a huge distance, so you are spinning with the Earth at about 1,000 miles per hour towards the east.
Okay, I'm with you. Equator is fast.
Now imagine someone standing at the North Pole. They're basically just pivoting in place. They have 0 rotational speed. They're just turning.
Pole is slow.
Right. Now imagine you are a parcel of air. You start at the equator and you start moving north. You are carrying that 1,000 mile per hour eastward speed with you. As you move north, the ground underneath you is slowing down. It's not spinning as fast anymore.
So you're moving faster than the ground.
You are still going east at 1,000 miles an hour. So relative to the ground, you start to pull ahead to the east, you curve to the right.
And the opposite happens if you come from the pole towards the equator.
Exactly. If you start at the pole, you have no eastward speed. As you move south, the ground underneath you starts racing to the east. You get left behind. So you appear to curve to the west, which is also a right-hand turn relative to your direction of travel.
So the simple rule is, in the northern hemisphere, everything moving curves to the right, and in the southern hemisphere, everything curves to the left.
That's the core of it. And this deflection breaks that simple north-south wind pattern into massive rotating cells. You get the trade winds in the tropics, which blow from the east, and you get the westerlies in the mid-latitudes, which blow from the west.
And the westerlies in the southern hemisphere are particularly famous. They're called the Roaring Forties.
They are. In the northern hemisphere, the westerlies are constantly running into land North America, Europe, Asia. Friction from the continent slows them down.
But in the south?
In the south, between 40 and 50 degrees latitude, there is almost no land. It is just open ocean all the way around the bottom of the world. The winds can just build up tremendous speed and power with absolutely nothing to block them. That's why sailors have feared the Roaring Forties for centuries.
So this massive global wind system is constantly pushing on the surface of the water, creating the major ocean currents. But on a more local level, the wind creates waves. And the text makes a really important distinction here that I liked. Between chop and swell, I surf a little bit, so I know this feeling, but I never really understood the physics behind it.
It's all about organization versus chaos. Waves are generated by the wind blowing over a patch of water. The area where the wind is actively blowing, say, a big storm in the middle of the Pacific, is called the fetch.
Okay.
Inside the fetch, it's pure chaos. You have waves of all different sizes, all different speeds, all different directions, all crashing into each other. That is chop.
It's a mess. You can't ride it.
It's a washing machine. But as those waves travel away from the storm, something amazing happens. Physics sorts them out. This process is called dispersion.
Dispersion.
Waves with longer wavelengths. The distance between two crests travel faster through the water than waves with shorter wavelengths.
So the big, long, powerful waves sprint ahead of the little ones.
Precisely. They outrun the small, jumbled guys. So the further the waves travel from the storm, the more organized and sorted they become. They form into these clean, rhythmic groups of waves with similar speeds. That is swell.
And that's the stuff surfers want.
That's what you want. A long period swell can travel from a storm off Antarctica all the way to California, thousands of miles, losing almost no energy until the very moment it hits the beach.
And when it does hit the beach, that's where the magic happens. The text talks about this process called shoaling.
Shoaling is the wave beginning to feel the bottom. As the water gets shallow, the bottom of the wave starts to drag on the seabed. Friction grabs it and slows it down.
But the top is still moving fast.
The top of the wave, the crest, doesn't know that yet. It's still moving at full speed. So essentially, the wave trips over its own feet.
That's a great way to visualize it.
The energy that was spread out in deep water starts to get compressed vertically. The wave bunches up, it gets taller and steeper, and eventually the top becomes unstable and just topples forward. That's the break.
And the shape of the seafloor determines the shape of that break.
Completely. If you have a gently sloping sandy beach, the energy bleeds off slowly. You get a spilling breaker, a rolling line of whitewater, good for beginners. But if you have a very steep coral reef, the bottom of the wave stops dead, and the top violently throws itself forward into a plunging breaker.
That's the tube, the barrel.
That's a famous barrel that surfers dream about.
Now, we can't talk about waves without talking about the monsters, rogue waves. For centuries, scientists thought sailors were just telling tall tales about these 50 or 60-foot walls of water that would appear out of a calm sea.
We did. We thought it was mathematically impossible based on normal wave statistics. But we were wrong. The text mentions that 1986 incident in the Atlantic, where a confirmed 56-foot wave smashed a ship, bent its foremast.
So how do they form?
We now know they happen because of a phenomenon called constructive interference.
This is the idea that waves can add their energy together.
Exactly. Imagine you have two different swell trains coming from two different storms, maybe thousands of miles apart. They're crossing each other's paths at an angle. Usually, their crests and troughs are out of sync and they kind of cancel each other out a bit.
Okay.
But every once in a while, purely by chance, the crest of a wave from storm A will line up perfectly with the crest of a wave from storm B at the exact same point in space and time.
So 1 + 1 = 2.
Or 1 + 1 + 1 can equal 3 or 4. The energy stacks vertically. For just a few seconds, you get a single peak that could be double or triple the height of the surrounding sea. A deep hole opens up in front of it, and this wall of water rises.
And then it's gone.
And then just as quickly, the waves pass through each other, and the monster vanishes back into the normal sea state.
Terrifying. Absolutely terrifying. Okay, let's move from the terrifying to something a little more beautiful, but just as complex. Section 4. The architecture of life. Coral reefs.
If the open ocean is a desert, then reefs are the oases. Or maybe the rainforests is a better analogy.
Yeah, feels right.
They cover less than 1% of the entire ocean floor, but they support something like 25% of all marine species. They are hotspots of biodiversity.
And the craziest thing is, this entire massive geological structure is built by a tiny, soft-bodied animal, the coral polyp.
The polyp is a very simple creature. It's essentially a stomach with a mouth, and that mouth is ringed by stinging tentacles. It lives inside a little limestone cup that it builds for itself by extracting calcium carbonate from the seawater.
So by day, it hides in its cup.
It hides, but by night, it extends those tentacles to catch tiny plankton floating by in the current. But it has a secret weapon. It's a farmer.
This is the amazing symbiosis with the zooxanthellae.
Right. Inside the actual tissue of the coral polyp live thousands of microscopic single-celled algae called zooxanthellae. It's the ultimate landlord-tenant relationship.
Okay.
The coral provides a safe, protected home and a steady supply of carbon dioxide from its own respiration. In return, the algae photosynthesize and create sugar-pure energy,
They pay their rent in sugar.
and they pay well. Up to 90% of the energy a coral needs to survive and build its skeleton comes directly from these algae. That's why corals can build such massive structures in these crystal-clear, nutrient-poor tropical waters. They are solar-powered.
But this partnership is incredibly fragile. The text talks about the phenomenon of coral bleaching.
Bleaching is basically an eviction. If the water gets too hot for too long, the algae inside the coral go into metabolic overdrive, and they start producing toxins that can harm the coral host.
So the coral kicks them out.
In an act of self-defense, it spits them out. The coral itself is actually transparent, so when the colorful algae are gone, you are seeing right through its tissue to the white limestone skeleton underneath. That's why it's called bleaching.
And without its tenants, the coral starves.
It begins to starve immediately. If the water doesn't cool down quickly enough for the algae to return, the coral will die.
We see these reefs in different shapes and forms all over the world, and Charles Darwin was actually the first one to figure out how they evolve over time, wasn't he?
He was. On his voyage on the Beagle, he realized that the different types of reefs tell a story of geological time. It starts with what's called a fringing reef.
That's coral growing right up against the shore.
Exactly. A new volcanic island pops up out of the sea, and coral starts growing in a fringe right on its shoreline. We see this in places like Hawaii or Moria in French Polynesia.
Okay, so that's stage one.
Stage one. But over millions of years, that volcanic island cools, it gets heavier, and it starts to sink back into the mantle, a process called subsidence. The coral, however, needs to stay near the surface for the sunlight. So as the island sinks, the coral just keeps building upwards, layer by layer.
So the island pulls away from the reef, and a lagoon opens up between them.
And that's a barrier reef. The Great Barrier Reef in Australia is the most famous example. It's separated from the mainland by a huge, shallow lagoon.
And the final stage is the atoll.
The atoll. This is when the island sinks completely below the waves. It's gone. All that's left is the ring of coral that kept growing up towards the light. It's this beautiful, circular ghost outline of where the land used to be.
Speaking of the Great Barrier Reef, the source material gives some pretty sobering stats. It's the size of Italy. It's the only living structure visible from the moon, but it's lost half its coral cover since 1985.
It's being hit by a devastating combination of factors. You have massive, repeated bleaching events from climate change, raising water temperatures. You have powerful cyclones that physically smash the reef structure to rubble.
And you have biological threats.
And you have biological threats, namely the crown of thorns starfish.
That starfish is like something out of a horror movie.
Yes.
It's huge, it's covered in toxic spikes, and it basically vomits its stomach out onto the coral to digest it alive.
It is a voracious coral-eating machine. And in recent decades, their populations have exploded in certain areas, wiping out huge tracts of reef.
But nature always has checks and balances. And that brings us to the giant triton.
The hero of the story.
The triton is a type of mollusk, and that's our next section, the inhabitants. We are focusing on mollusks because they are just so incredibly diverse.
They really are. You have over 73,000 known species. On one end of the spectrum, you have a microscopic snail. On the other, you have the giant squid. But they all share a basic toolkit, a soft body with a layer of skin called a mantle, a muscular foot, and usually a radula.
The radula is my favorite piece of animal biology. It's described as a rasping tongue, but that sounds way too gentle. It's a chainsaw tongue.
It really is. It's a ribbon covered in rows and rows of microscopic teeth made of chitin, the same hard stuff as an insect's exoskeleton. In some predatory snails, these teeth are even hardened with iron or magnetite.
Let's look at the dog whelk. It looks like a harmless little sea snail you'd find in a tide pool, but it's a cold-blooded murderer.
The dog whelk is a specialist predator. that feeds on barnacles and mussels. It climbs on top of its victim, finds a weak spot, and then uses that radula to drill a perfectly circular hole right through the shell.
How long does that take?
It can take days of constant scraping. Once the hole is drilled, it injects digestive enzymes that turn the mussel into a soup, and then it just sucks out the contents.
It's basically the movie Alien, but in super slow motion.
A very good comparison.
Hmm.
Then you have a totally different strategy with the common limpet. These guys aren't hunters, they are grazers. But they are incredibly territorial about their personal space.
The home scar.
The home scar. A limpet will find a spot on a rock and use the edge of its own shell to grind a groove that fits it perfectly. It creates a perfect vacuum seal so it doesn't dry out when the tide goes out.
And it always goes back to the same spot.
It goes out to graze on algae, sometimes traveling several feet, navigating the rock, and then it returns to that exact millimeter-perfect spot every single time.
I love that. It's like having a designated parking spot that has been custom molded to your car.
It's exactly.
Then there's the tiger carry. You see these beautiful, polished, shiny shells in souvenir shops. But in the wild, you almost never see the shell.
Because the animal is shy about its shell. It extends its mantle, its soft, fleshy skin, all the way up and over the outside of the shell, completely covering it.
Why does it do that?
The mantle is fuzzy and covered in spiky projections called papillae. It protects the shell from scratches and growths, keeping it glossy. It's also thought to help with respiration. It's like putting a protective cover on your brand new car.
And we have to talk about the masters of the mollusk group. The cephalopods, squid, cuttlefish, octopuses. They're mollusks, too. They're basically snails that traded their shell for speed and brains.
And for the best camouflage in the entire animal kingdom, they have specialized cells in their skin called chromatophores.
Chromatophores.
Each one is a tiny sac of pigment red, yellow, brown, surrounded by little muscles. The brain sends signals directly to these muscles. They can expand a red sac to create a red dot, or contract it to make it disappear.
So it's like a biological TV screen.
It's like high-definition organic television skin. They can change color, pattern, and even texture in the blink of an eye to match their surroundings perfectly, or to create dazzling displays to communicate or confuse prey.
And they get around with jet propulsion.
Yes, they suck water into their mantle cavity and then blast it out through a steerable funnel called the siphon. They can aim the siphon to move in any direction. It's biological rocketry.
Before we leave the biology section, there were a couple of other cool facts from the source material I wanted to touch on. The golden jellyfish of Palau. These things have lost their sting, for the most part, right?
Mostly, yes. They live in a unique, landlocked marine lake called Jellyfish Lake. Because they have no major predators in this isolated environment, they've evolved to have a very mild, almost unnoticeable sting.
But they've evolved a new behavior.
A totally new behavior. Like the corals, they have algae living in their tissues. So every single morning, millions of these jellyfish migrate together from one side of the lake to the other, following the arc of the sun across the sky to give their internal algae the best possible light for photosynthesis. Then they swim all the way back at night.
They're living solar panels. They're farming within their own bodies.
Exactly.
And the polar bear, the text lists it as a marine mammal, which I guess makes sense.
It absolutely does. Its scientific name is Ursus maritimus, the sea bear.
Yeah.
They are excellent swimmers, capable of swimming for days at a time across vast stretches of open ocean. They've even evolved specialized valves in their nostrils that close automatically when they go underwater.
They are the apex predator of the sea ice, but they are truly creatures of the ocean.
They are.
Okay, we've covered a lot of the small stuff and the general principles. Now I want to zoom out to a specific region. The text takes us on a tour of the North Pacific, the Bering Sea and the Gulf of Alaska. This feels very, very different from the tropical reefs we were just talking about.
It is a completely different world. It's cold, it's often storm-tossed, and it is incredibly productive. But it's also a place of violent geology. This is the heart of the Ring of Fire.
The Bering Sea is defined by that long chain of islands, the Aleutians. Looking at the map, it's this perfect arc of islands swinging out from Alaska towards Russia.
That arc is a textbook example of a subduction zone. The massive Pacific plate is crashing into the North American plate and diving underneath it. As that plate dives down into the mantle, it melts, and that molten rock rises up to form volcanoes.
And that's the Aleutian Island chain.
A chain of active volcanic islands born from the collision of continents.
But the Bering Sea wasn't always a sea. This is the incredible story of the land bridge.
Beringia. During the height of the last ice age, so much of the world's water was locked up in massive continental glaciers that global sea levels were almost 400 feet lower than they are today,
400 feet.
which was enough to expose the very shallow continental shelf that connects Russia and Alaska.
And this wasn't just some narrow, muddy bridge, was it?
No, not at all. It was a huge subcontinent. It was hundreds of miles wide. Geologists think it was a vast, grassy steppe teeming with woolly mammoths, giant bison, and horses. And crucially, with humans. This is the highway that allowed the first people to migrate from Asia into the Americas.
And when the ice melted and the water rose, that entire world just vanished beneath the waves.
It vanished. And now it's one of the richest fisheries on the planet.
The source says it produces about half of the entire U.S. fish catch.
Pollock, crab, salmon. It's so rich because of that green water we talked about earlier, massive nutrient upwelling driven by the powerful storms and currents in the region.
Further south from there, we have the Gulf of Alaska. And here, the text points out the existence of seamounts. These are underwater mountains.
Specifically, the Kodiak-Bowie Seamount Chain. And these are fascinating because they form in a totally different way than the Aleutian volcanoes. They are formed by a hotspot.
Like Hawaii.
It's exactly like Hawaii. There is a stationary plume of superheated magma punching up from deep within the Earth's mantle. In this case, it's called the Cobb Hotspot. The tectonic plate, the Pacific plate, is moving over it like a conveyor belt.
So the hot spot stays in one place and the plate moves over it.
Right. The hotspot punches a hole in the plate, builds a volcano, and then the plate moves on. The volcano gets carried away from its magma source, goes extinct, and eventually erodes down into an underwater seamount, while a brand new volcano starts to form behind it. It creates a perfect line of mountains that shows you the exact direction the plate has been moving for millions of years.
And we can't talk about the Gulf of Alaska without mentioning the Exxon Valdez.
1989. Bligh Reef in Prince William Sound. The oil tanker ran aground and spilled what the source says was 30 million gallons of crude oil, though some estimates are lower. It was an absolutely devastating wake-up call about how fragile these cold water ecosystems are.
Why are they more fragile?
Because oil breaks down very, very slowly in cold water. The bacteria that eat oil work much less efficiently. You can still dig into the sediment on some of those beaches today, decades later, and find pockets of toxic oil.
And finally, we move down the coast to the Cascadia Basin, off the coast of Washington, Oregon, and Northern California. This is a geologically scary place.
This is the Cascadia subduction zone. You have the small Juana Fuca plate, a remnant of a much larger ancient plate diving under the North American continent, and right now it's stuck. It's locked by friction.
So pressure is building.
Stress is building up every single day. The plates are trying to move, but they can't. The North American plate is actually bulging upward.
And eventually it's going to unzip.
And when it unzips, you get what's called a megathrust earthquake, a magnitude 9.0 or higher. The last one happened in the year 1700.
How do we know the exact year?
We know because it sent a massive tsunami across the entire Pacific Ocean that wiped out coastal villages in Japan. And they have meticulous historical records of this orphan tsunami, a giant wave that arrived without any earthquake being felt locally.
So the pressure has been building for over 300 years.
Exactly.
Yeah.
It's a stark reminder that the ocean floor is not static.
Yeah.
It's active. It's moving. And it has the power to reshape our coastlines in an instant.
Wow. We've covered a lot of ground today, or I guess a lot of water. We've gone from the hydrogen bonds holding a single water drop together to the tectonic plates moving entire continents. We've seen the microscopic algae that feed the world and the massive rogue waves that can sink ships.
It's a lot to take in, but I think if there's one single synthesis here, it's interconnectedness. You can't separate the biology from the chemistry or the chemistry from the geology. The volcanoes provide the water and the salt. The spin of the earth and the heat of the sun drive the currents that distribute the oxygen. And the life itself balances the chemistry of the entire system. It's all one machine.
It brings us right back to that Fabien Cousteau quote from the beginning. Every act each one of us takes affects our planet's water cycle.
It's not just a nice sentiment. It's a physical reality. The plastic you drop on the street washes into the storm drain, which goes to the river, which feeds the ocean. The excess fertilizer used on farms in the Midwest washes down the Mississippi River and creates a massive dead zone in the Gulf of Mexico.
We are part of this system. We are not external observers.
Not at all.
He has that great closing line in the foreword. It would be much healthier for us to learn to dance nature's waltz than to try to change the music.
I love that. We've spent a lot of the last century trying to force the ocean to do what we want, overfishing, polluting, building concrete walls on the coast. But the ocean is too big, too powerful, and far too complex for us to control.
We can't change the music.
We have to learn the steps. We have to learn how it works, how the currents flow, how the reefs grow, how the fish reproduce, and then fit our own lives into that rhythm.
We need to be better dance partners.
Precisely. And that starts with understanding the music, which is what we tried to get a little closer to today.
Well, I certainly look at that glass of water on my desk a little differently now. It's not just a drink. It's a universal solvent, a dipolar magnet, and a traveler from the dawn of time that might have come here on a comet.
Planet Ocean. It's a wild place.
Thanks for diving in with us. We'll see you on the next one.